All right, let's talk about friction. So, what is friction? Well, friction is the resistance to relative motion between two bodies. This word relative is important, and we'll talk about it. But this is, I guess, my first definition of if someone asked me what friction was, I'd say it's that resistance to relative motion between two bodies. So, what causes friction? Well, that's a good question. I didn't have a great answer, so I went over to my manufacturing textbook and I found two theories of friction that I read just a little bit about. There's this adhesion theory of friction, and then there is this abrasion theory of friction. So, for the adhesion theory of friction, from what I understood, if you have two surfaces, say we have this blue surface on the top and this green surface on the bottom, and we zoom in really, really, really close to where they actually contact each other, it's going to look something like this. It's the surfaces are very irregular on this scale when you get super close. So they're very jagged. They're very jagged, a lot of peaks and valleys, and both surfaces are like that. And so because of this, they only contact in a few points, right? They're called these contacting peaks, right? So you can see wherever these red dots are, they're contacting here on these irregular surfaces. And these are called the real areas of contact. And the entire load between these two surfaces is supported at these contacting peaks, right? And since these real areas of contact are really, really small, the peaks become really highly loaded, right? Because you have a load on a very small area. So they become highly loaded at these peaks, which results in micro welds, and this causes the peaks to also form adhesive bonds. And the strengths of these bonds can depend on a couple things like surface material of the metal, the temperature, surface condition, things like that. Right? So you have to overcome these adhesive bonds and micro welds and stuff in order to have these two surfaces slide against each other, and that's friction. Okay, so abrasion theory of friction. This one's a little easier for me to understand. If one surface is harder than the other surface, then the harder surface will scratch and gouge into the softer surface, right? And this is known as plowing. And you can think of this as like it's like what it sounds like. If you have a tractor in a field and it's pulling a plow behind it that's turning up the earth, right? That metal plow is digging into the soft earth, and that's the same concept as like two surfaces of a metal on touching. You know, if one's harder than the other, the harder one's gonna plow and scrape into the other one, and that's gonna cause friction like that. Now, it's good to kind of know these theories on a high level, I guess, because you can kind of guess on how to lower friction if you want to lower friction, or increase friction if you want to increase friction. For me, most of the time, I just think of friction as a mechanism that takes energy away from my system, and it's usually in the form of heat, right? I always think of these dynamics problems as, you have buckets of energy, and some things add energy into these buckets, and some remove energy. Well, friction is something that takes energy away from our system. So in dynamics, we usually deal with two types of friction: Coulomb friction, which is also known as dry friction, and then viscous friction, which is the friction as an object moves through a fluid. Now, these are the two popular ones that I commonly come across, but note that there are a lot of different models of friction. Friction is a very hard thing to model or guess, I guess. Most of the time, when you're in industry, you'll run tests. You'll run tests and you'll correlate your models, especially friction, because it's such a hard thing to like nail down. You'll get those parameters from test data, from experimental data. But in a theoretical point of view, we can just, we'll focus on, what we're going to talk about here. Okay, so Coulomb friction. So there are two types of Coulomb friction. And remember, Coulomb is the dry friction, dry. There's static Coulomb friction and dynamic Coulomb friction. So say you have a heavy box on a frictionless surface, and you applied a force to it, right? So we have our box, it is in contact with the ground, which is frictionless, very important, and we're applying a force to the right, in this case in the positive EX direction. If we drew our free body diagram, it would look something like this, right? We would have gravity pulling the box down, and then we would have an equal and opposite normal force, because the normal force is what keeps our box from just going through the ground to the center of the earth, right? That's what keeps it on the ground, the normal force. That counteracts gravity. And then we have our force that we're applying to the box, and that's it, right? There's nothing countering our force, F, this purple force. So there's this imbalance, right? There's this imbalance in the EX direction. So that means no matter how small the force is, as long as it's non-zero, that force will cause the box to move to the right. And this is because there's no force to counter it. So even if this box is like 1,000,000 pounds, right? And you had like a bumblebee blowing on the box, trying to push it to the right, that force is really small, but it's still a force to the right, right? So that box slowly, very slowly, is going to move to the right. Okay, so now, if we introduce Coulomb friction, then the free body diagram would look something like this, right? So now we have something opposing opposing this force F, this purple F, right? It's going in the opposite direction of the velocity of the box. So if the box is trying to move this way, friction is opposing it this way. So now, with friction in the picture, the box will not necessarily move to the right with, some arbitrary amount of force, right? First, the force has to be large enough to overcome the Coulomb's static friction, right? And this static friction force is given as this right here, where mu sub s is the coefficient of Coulomb friction, and the magnitude of n, that is the normal force. That is this force, the magnitude of n. And once this inequality, notice it's an inequality, it is not, the static friction isn't just equal to something, right? It's an inequality. If it's less than this, then it's not moving. But once this inequality is violated, then the box in our example will begin to slide. It will begin to slide. I talked about this. Magnitude of the normal force, that's n. Mu sub s, this is the coefficient of static Coulomb friction. You can just Google it. There's different values for the static coefficient, and it depends on what the two materials you're working with are, right? So if you have aluminum on aluminum, that'll have a mu sub s associated with it. If you had steel on aluminum, that'll have another thing, right? There's a bunch of different combinations of materials, and also, if it's lubricated or not lubricated, that'll also change mu sub s. But yeah, there's plenty of tables online that talk about this. Mu sub s is the coefficient of static friction. Okay, so say you violate this inequality, and now you're sliding. So once the box is sliding, then it's experiencing dynamic Coulomb friction, which is given as this equation right here. And let's break this down. So this is our free body diagram right here. We have our force pushing to the right. We have our friction opposing the motion of the box. We have our normal force, and we have gravity. What is this equation saying? This equation, let's look at this right here first. We're going to talk about what vrel means, but just for now, know that the box is moving to the right. Okay, so the velocity is to the right. Well, we already learned this. We did this quite a few times, but if you take a vector and you divide it by the magnitude of itself, that creates a unit vector pointing that's parallel to, the vector you're working with, right? So if vrel is pointing to the right, then vrel divided by the magnitude of vrel is just a unit vector pointing in the direction of vrel, right? It's a direction component. This is a direction component. And you'll see we have a negative out front, so I think of this as being all together. I think of that negative kind of being with our direction component, right? Because the force of friction is always going to oppose motion, right? Friction never aids in pushing the box forward. It's not, the force is never going to be like this if the box is moving this way. If the box is moving this way, friction is pointing in the opposite direction. If the box were moving this way, friction points in the opposite direction. It's always pointing opposite to the velocity, the relative velocity of the box with the other surface or whatever it's sliding with respect to. All right, mu sub d, coefficient of dynamic Coulomb friction. Again, this is just a number. Mu sub s and mu sub d are usually taken from experiments, experimental data. N, normal force, magnitude of the normal force. So our force of friction, our force of dynamic friction, and also static friction, is really dependent on only this N, this magnitude of the normal force. This is kind of the key of Coulomb friction, the magnitude of N. That is what determines how big this F is, right? It really doesn't matter how fast the surface is sliding. It doesn't matter how fast it's sliding on the surface. It matters how big the normal force is, right? And this is going to be different from viscous friction when we look at that, but just keep that in mind. Now, let's look at an example to better understand this VREL idea. So if we're pushing a box on a conveyor belt, so here's our little man, he's pushing his box on a conveyor belt. So if I'm pushing the box at 3 miles per hour to the right, and the conveyor belt is moving, at 5 miles an hour, then the absolute velocity of the box is 8 miles an hour to the right, right? I'm pushing 3 miles an hour, but I'm also standing on the conveyor belt, which is going at 5 miles an hour. So in total, I'm going 8 miles an hour, right? We talked about this in our, addition theorem of angular velocity. It's the same idea. This is linear velocity. So, however, the relative velocity, right? 8 miles an hour is the absolute velocity of the box, but the relative velocity between the belt surface and the box is 3 miles an hour, right? So VREL is how fast one surface is moving with respect to the other. If I was not pushing the box at all, this box would just be sitting on the conveyor belt, moving to the right at 5 miles an hour. But they would not be sliding between each other, right? It's only when I start pushing on the box on the conveyor belt at 3 miles an hour that our box starts sliding on the conveyor belt, right? So I think that's good. Just VREL, the relative velocity, is how fast one surface is moving with respect to the other surface. It is not the absolute velocity, which we've been working with a lot. It is the relative velocity. All right. Viscous friction. This is the equation for viscous friction, or one of the equations you could use. Negative C VREL, where C is the coefficient of viscous friction. Again, this is something that usually comes out of experimental test data. I'm sure there's tables for this coefficient. I've also used a nonlinear version of this where it's CV squared. Just look at the technical document of whatever you're working on and it'll tell you. But let's just say negative C VREL. Now, this is the big difference between Coulomb friction and viscous friction. Viscous friction is directly proportional to the velocity. The relative velocity. Remember before when we were talking about Coulomb? This is just a unit vector. Coulomb friction didn't care how fast it was sliding on the surface. It only really cared about this normal force. But in viscous friction, you do care, right? How fast you're moving through that fluid matters, right? And again, negative. It's in the negative direction. Negative VREL is how you can think about it. What did I say here? Notice that the viscous friction is directly proportional to VREL. Yeah, okay, I said that. Dynamic was only dependent on magnitude of N. Yeah, okay. And this is just an equation. That's it. It's just a force. And we're gonna do examples with both of these, viscous and Coulomb friction and stuff like that, to become comfortable with it. I'm just introducing the topic now in this video. Some applications of friction. Why do we even care? Here's three examples I thought of. How does a car stop? At least an internal combustion engine car, not an electric vehicle that has regenerative braking, but an internal combustion engine car needs to stop with a brake pad, right? A brake pad. So you have this caliper here, and the caliper has brake pads on it that squeeze this. Oh my god, I don't know anything about cars, but it squeezes this disc or rotor. I guess is maybe where a disc. I'll call it brake disc. Maybe that's what it's called. The brake pads squeeze against this brake disc, cause friction, dissipate energy in the form of heat, which slows down the car. And so, if you're sitting at a stoplight and you have your foot on the brake, you want to make sure that the coefficient of Coulomb static friction is high enough that your car is not going to roll forward, right? And the surface between the brake disc and the brake pad do not slide, right? So there's an application of the static Coulomb friction. And if you're going very fast and you want to slow down, you want to make sure that the coefficient of dynamic Coulomb friction is tuned such that you can actually stop the car, right? And that you can provide a high enough normal force to squeeze the plate, squeeze that disc plate to slow the car down. This was a dumb example, but if you rub two sticks together, the reason they get hot and create a fire is because of friction between the two sticks. Here's an example that I commonly come across quite a bit for viscous friction is a some kind of a hydraulic damper, right? So you'd have this casing that's filled with some kind of fluid, and then you have this rod, this piston rod, with some face right here, and you can actually dissipate energy out of a system by forcing this rod through that liquid. And when you do that, due to viscous friction or viscous damping, it's going to take energy away from the system and slow it down. Yeah, so that's the bottom. And that's everything I want to say about friction right now. We'll do some examples in the future, and I'll see you in the next one. All right, bye.